Selective precipitation. A solution containing several different cations can often be separated by addition of a reagent that will form an insoluble salt with one of the ions but not the others. A successful reagent can precipitate with more than one of the cations as long as their equilibrium constant Ksp value are significantly different. So as an example, what is the hydroxide ion concentration just slightly above which magnesium hydroxide will begin to precipitate from seawater? The concentration of magnesium ion in seawater is 0.059 molar, and the Ksp for magnesium hydroxide is 2.06 times 10 to the minus 13. So calculate the hydroxide ion concentration required for the Q value to equal Ksp, and then slightly more than that will result in precipitation. Turn your playback off, try it, and come back. Here's the solution. We just write our mass action equation for magnesium hydroxide. We're given the concentration of magnesium ion as 0.059, so we simply solve for hydroxide ion concentration, and it comes out to be 1.9 times 10 to the minus 6. What is the magnesium ion concentration when calcium at 0.011 molar just begins to precipitate from seawater as calcium hydroxide? And here's the Ksp of calcium hydroxide, 4.68 times 10 to the minus 6, and magnesium hydroxide is 2.06 times 10 to the minus 13. So it's pretty obvious that magnesium hydroxide is much more insoluble than calcium hydroxide. Well, to solve this, first we'll calculate the hydroxide ion concentration at which calcium hydroxide begins to precipitate. So the Q equation is the concentration of calcium ion times the concentration of hydroxide ion squared. And at equilibrium, Q equals Ksp. So we plug in 0.011 for calcium ion, we solve for hydroxide ion, and we get 2.06 times 10 to the minus 2. So we've established that the calcium hydroxide begins to precipitate when the hydroxide ion concentration is 2.06 times 10 to the minus 2 molar. Now, use this hydroxide ion concentration when calcium begins to precipitate to calculate the magnesium ion concentration. And the Ksp for magnesium hydroxide is 2.06 times 10 to the minus 13. So we plug in the hydroxide ion concentration when calcium hydroxide begins to precipitate. We solve for magnesium ion, we get 4.8 times 10 to the minus 10 molar. So when calcium ion just begins to precipitate out as calcium hydroxide, the magnesium ion concentration has dropped from 0.059 molar to 4.8 times 10 to the minus 10 molar. Okay, let's talk about qualitative analysis, an analytical scheme that utilizes selective precipitation to identify the ions present in a solution is called qualitative analysis. And it utilizes wet chemistry rather than instrumental analysis. You're going to be doing this in lab if you haven't already started. A sample containing several ions is subjected to the addition of several precipitating agents. And then addition of each reagent causes one of the ions present, or a class of them, to precipitate out. So here's a schematic. Let's say you have a solution containing cations A, B, and C, and you add the first precipitating agent, which reacts with cation A to form a solid precipitate, leaving behind in solution the cations B and C. Typically you centrifuge the test tube, which drives down the precipitate to the bottom of the test tube. Then you decant off the liquid portion, and now you have B and C, and you have cation A in the solid form of whatever anion it reacted with. So then you do the same thing with a second precipitating agent and you get cation B precipitating out. And after that occurs, you have a solution containing only cation C. So how would that look in reality? Well, you might have a solution with a mixture of ions. Probably wouldn't have all of these, but you'd have some of these mixed together. And you need to separate them out and confirm which ones are there and which ones aren't. The group 1 cations are the insoluble chlorides. Silver, mercury +1, and lead ions are all insoluble with chloride. So if you add 6 molar hydrochloric acid to your initial solution, only the group 1 cations precipitate out as their chlorides. And you spin it and separate them out. Now your solution has the remaining cations. The second group contains the very, 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 very insoluble sulfides. Copper sulfide, bismuth sulfide, cadmium sulfide, lead sulfide, etc. And what you do is you add a reagent that generates hydrogen sulfide, but you do that in a 0.2 molar solution of hydrochloric acid. And what that does is to limit the concentration of sulfide ions. So only the very, 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 very insoluble sulfides in group 2 are going to precipitate out. Now you're going to add hydroxide ion to that mixture, and you're going to get a mixture containing hydroxides, aluminum, iron, and chromium hydroxides, and the remaining sulfides, zinc sulfide, nickel sulfide, cobalt sulfide, etc. And then you work on that to separate those out. And finally, you have the remaining cations are going to react with ammonium phosphate to form the insoluble phosphates: barium phosphate, calcium phosphate, magnesium ammonium phosphate. Group 5 is what's left over, and they don't really form precipitates with anything, no way, no how, nuh-uh, and that's the alkali metal cations. Now let's talk about the equilibria involved with complex ion formation. Transition metals tend to be good Lewis acids, and they often bond to one or more water molecules to form hydrated ions. Water is the Lewis base, donating a pair of electrons to form coordinate covalent bonds. That's where one species provides both electrons in a covalent bond. So we have silver ion plus 2 water molecules reacting to form the hydrated silver ion. Ions that form by combining a cation with several anions or neutral molecules are called complex ions, like, for example, this hydrated silver ion. The attached ions or molecules are called ligands. So the water in this case is called a ligand. If a ligand is added to a solution that forms a stronger bond than the current ligand, it will replace the current ligand. So if you take hydrated silver and react it with ammonia, the ammonia will form a stronger complex ion and kick off the water molecules and react with the silver cation itself. And generally when we write hydrated metal cations, where water is the ligand, we don't include water since its complex ion is always present in aqueous solutions. So we simply write it this way and we don't show the water forming a complex ion. Now let's talk about the formation constant. The reaction between an ion and ligands to form a complex ion is called a complex ion formation reaction. So when we have silver reacting with ammonia to form the silver ammoniacal complex ion, the equilibrium constant for the formation of this reaction is called the formation constant, or Kf. And if you notice, this is precisely the reverse of what we've been doing with dissociation constants. Here we have two species coming together to form a complex ion, rather than disassociating into separate ions. The mass action equation, since all of these are in aqueous solution, is going to be products over reagents to the power of their coefficients. Therefore, we have the silver ammoniacal in the numerator, the concentration of silver ion in the denominator, and the concentration of ammonia in the denominator squared, because it's 2 ammonia molecules reacting with 1 silver. As you can see, the formation constant here is 1.7 times 10 to the plus 7. That means this reaction is very favorable toward the product side and is almost a complete reaction toward the product side. In fact, if we look at formation constants of selected complex ions, we see extremely large Kf values. So now let's do a problem involving formation constants. 200 milliliters of 1.5 times 10 to the minus 3 molar copper nitrate is mixed with 250 milliliters of 0.2 molar ammonia. What is the concentration of copper ion at equilibrium? So first we write the formation reaction and the Kf expression. It's going to be copper ion plus 4 ammonia molecules forming the copper amine complex. Kf equals products over reagents to the power of their coefficients. Now we determine the concentration of ions in the diluted solution. Because we're mixing 2 solutions together, the molarity of both the copper and the ammonia is going to change. For the copper ion, we have 0.2 liters times 1.5 times 10 to the minus 3 moles per liter. So that will be moles of copper plus 2, and we divide that by the new total volume, which is going to be 0.45 liters. So dividing that through, that gives a concentration of 6.7 times 10 to the minus 4. We do the same thing with the ammonia, finding the moles of ammonia, and then dividing again by 0.45, the new total volume. That's going to be 1.1 times 10 to the minus 1, or 0.11 molar. So continuing our problem, the copper ion, as we just calculated, is 6.7 times 10 to the minus 4 molar. The ammonia is 0.11 molar, and our reaction is each mole of copper ion that reacts with 4 moles of ammonia to form the copper ammoniacal complex. And the mass action equation, Kf, equals a very, very large K value of 1.7 times 10 to the minus 13. So now we're ready to fill out the ICE table. Here's our copper ion, our ammonia, and our complex. When we start initially, we have 6.7 times 10 to the minus 4 of the copper ion, 0.11 molar of the ammonia, and since nothing has reacted yet, 0 of the complex. Now what reacts? Almost all of the copper ion reacts, and we know that because the K value is such a large number. Certainly almost all the copper ion is going to react, but it's going to leave behind a very small amount that we're going to call X at equilibrium. For the ammonia, 4 times that amount is going to react, and it's going to form 6.7 times 10 to the minus 4 molar of the complex. So at equilibrium, we have that trace amount of copper ion X. We have almost 0.11 of the ammonia. This is a very small number, and subtracting it from 0.11 leaves us with 0.11 approximately. And then equilibrium value of the complex ion is 6.7 times 10 to the minus 4.